Well, see, dear students, we have two types of specific heat for gases. CV, which is defined as specific heat at constant volume, and CP, specific heat of gas at constant pressure. Now we can define this CV and CP by using this equation. Suppose that we have a system like this. Uh, Suppose that we have a constant volume system. This is a rigid container. This is a rigid container, right? Volume is fixed, right? And we have taken 1 mole of gas. 1 mole. 1 mole of, suppose that we have taken helium, right? And our aim is to increase the temperature from T Kelvin to T plus 1. So what we want? We want to increase the temperature by 1 degree, right? 1 degree. So means we can say that in this equation 3, from equation 3, we can write from equation 3, what we can write, that N is equal to 1 mole and delta T is equal to T plus 1 minus T. So this is equal to 1 Kelvin, right? Or 1 degree, because the difference is same at both the scales, so no problem. So whatsoever heat is required, see, if delta T is equal to 1 and N is equal to 1, then CV is equal to Q. So at constant volume, this is a constant volume system. So at constant volume, whatsoever heat is required, delta Q V at constant volume, whatsoever heat is required to raise the temperature of ideal gas by 1 degree is known as specific heat at constant volume. So we can define here the amount of heat required to raise the temperature, or to change the temperature, raise the temperature by 1 degree, 1 degree Celsius or 1 Kelvin, of 1 mole of gas, or ideal gas you can write, 1 mole of ideal gas at constant volume. At constant volume, is known as CV, is specific heat at constant volume. And you know why I have specified this helium here means in place of helium if you take hydrogen, so different heat is required, means CV is different for that. If you take nitrogen, then a different heat is required, means CV is depends on the nature of the gas. If volume is constant and everything is fixed, then CV will change with the nature of the gas. Means the magnitude of CV. So this is the definition of CV, and this CV basically this depends on the nature of gas. Means for gas to gas it is different, and in the beginning of heat capacity or specific, I have already told you that it depends on the nature of the matter, right? It depends on the nature of the matter, means if you take iron in place of aluminium, then heat capacity or specific heat is different. So this is CV. Similarly, what is CP? For CP, if we take, I mean, same gas, everything I'm taking, everything is same. The only difference is now I'm taking constant pressure system. So, how to design a constant pressure system? See, constant pressure system, how to design? Constant pressure system you can design like this. Put a massless and frictionless piston over a container. So if you put a massless frictionless piston over the container, then then you will get the constant pressure system. So suppose that we have a container like this, and we have put the piston, and this time also 1 mole helium I have taken, and at T Kelvin, right? Now we put some heat to this system, QP I am putting this, then what will happen? See, when this constant pressure system is there, then what first you analyze your system. See here, the gas molecule will apply the pressure on the piston. This wall is the rigid, only this can be shifted, and outside pressure basically P external, this time P external and P gas is same. Means whenever you put this massless and frictionless piston, every time the pressure of the gas is equal to the external pressure, and you can say this is equal to the P atmospheric, because this is piston is massless and frictionless, there is no mass of this piston. So every time this P external is equal to atmospheric pressure, so the pressure of the gas is equal to the atmospheric pressure. Clear to everybody? Okay, good. So this is initial state of our system before providing this heat. So pressure of gas is equal to external pressure. This is our initial state. Now what will happen when you when you provide heat to the system? Pressure will increase. Once pressure will increase, the pressure difference created, means this piston will shift above. Now analyze each and every point when you are putting heat to this system. This heat will change the temperature of this gas and do one more thing here. What? This will push the piston above because pressure increase, temperature increase, pressure increase, but since this piston is massless and frictionless, so once you put a little heat, means this heat will expand in two ways. Whatever heat you are giving, that will expand in two ways. Number one, to increase the temperature, to increase the temperature, and work against external pressure. External pressure. Which type of work? PV work, PV expansion work. All of you are getting my point or not? Under constant pressure system, whenever you provide heat, this heat will, utilizes in two ways. First, to increase the temperature, and second, to expand the, to push the piston above. So what will happen? So now, so this time the piston will shift little bit. Gas will expand, and now let the temperature is T plus 1, because we want to increase the temperature by 1 degree only. So so this time delta QP is equal to 1 mole into Cp into delta T. Delta T is equal to 1 here. So this is equation here. Delta QV is equal to 1 mole into Cv into delta T is 1. So this is equation 1 here, and this is equation 2. Now let me know that what is the relation between this delta Q, it means heat supplied to the system at constant volume, and heat supplied to the constant pressure. What is the relation between these two Q? You just observe here, there is no work. This heat is consumed to increase the temperature only, because the volume is fixed, the container is rigid, there is no piston, there is nothing to, possibility for the expansion of the gas. But here, when you provide the heat, there is a chance of expansion because it's a constant pressure system, And as per the equation of state, all of you are knowing, if you are increasing the temperature, if you are increasing, giving the energy to the system, pressure also increases, temperature also increases. So temperature, along with temperature rise, due to increase in pressure, there is a pressure difference between system and surrounding, and some expansion work will take place, right? So in QP and QV, you have a direct relation. There is no mathematical proof is required, only just common sense you can use, right? So this, since QP, more heat is required to raise the temperature of the same gas, 1 mole of gas, 1 mole of same gas by 1 degree. So means if you are heating, if you want to, if you wish to increase the temperature of a gas by 1 degree, so under constant volume condition, different heat is required, and under constant pressure is different heat is required, and under constant pressure more heat is required to raise the temperature by 1 degree of the same gas. So since QP is more than QV, thus you can write Cp is more than Cv for a given gas. For a given gas. Right? So this is an important relation. Now, what we can write here. Now see, I am not using any formula. I am just using the, logic, just logic, nothing, no specific formula. I am not going to use the differential formula for derivation of this. No, not required. You just see within one line we can prove Mayer's formula. See what we can write here: Cp minus Cv. What do you think? What is equal to this difference, Cp minus Cv? See, to increase the temperature by 1 degree, 1 degree Celsius, same heat is required whether you are taking constant volume or constant pressure. The only difference is that work against a constant external pressure, this energy equivalent to this is added into the Cp. So Cp minus Cv is equal to, you can write, work done by the gas per degree rising temperature. Per degree rise in temperature. So this is equation 3, right? Now see, we can calculate this work. We have this formula, equation of state, PV is equal to nRT. I have taken n is equal to 1 mole. So we can write PV is equal to RT. So we can write very simple, delta PV is equal to delta RT. We can write, right? Okay. Now, under constant pressure condition, what we can write? Del P delta V. This is equal to, this is constant, so you can write R delta T. And all of you are knowing that this P delta V is the work, PV work, right? So see, we don't know what is the initial volume here. We don't know what is the final volume here. So we cannot use this formula to evaluate the work. But P delta V is always equal to R delta T for 1 mole of the gas. And right hand side we have this value delta T. See, delta T is the 1 degree. Increase the temperature by 1 degree. So we can write here the work done by the gas per degree rise in temperature. So this work done is equal to P delta V is equal to R into 1 degree Celsius or 1 Kelvin, means the work is equal to PV work which is taking place in this constant pressure condition, that is equal to R, right? So this is also a formula for calculation of work. If you do not know the pressure and volume change, but if you have temperature change, then you can put this. And you know this is a constant pressure condition, so here I am taking P delta V is equal to R delta T, N is equal to 1 mole, right? So this is you can equate this. So the work done in this case, but this work done, I mean for energy for this work done is provided by the external source heat Q. What Q we have provided. So part of Q is converted into temperature change, and part of Q what we have provided under constant pressure condition, that is consumed to the raise the temperature. So you can write Cp minus Cv is equal to R. What this looking here, if you see here R, only R, but you know this I mean basically this is not exactly R, this is what, N into R into delta T. Since N is equal to 1, delta T is equal to 1, so this is basically R. So this appears like this, but actually this is this, right? So Cp minus Cv is equal to R. R you can write this general formula, and this formula I have written with the common sense. This formula you won't find anywhere in the book. You will always find this formula, and the people are directly deriving this formula. No need to derive. You just put the logic and apply the concept, and you will get this formula, right? So basically this is for 1 mole. Suppose that if n mole is there, right, then what will be the formula? Suppose that if n moles are there, then what is the formula? Cp minus Cv is equal to what? So this is for 1 mole, so we can write this. Now for n mole, so Cp minus Cv is equal to nR. This is equation 6 you can write. So this is for 1 mole. For 1 mole, this is for n mole, right? Suppose that now this Cp is the means specific heat, right? For n mole, Cv for n mole, so here this you have to put nR. And if it is asked, okay, for 1 gram of the gas, what is the formula? This formula, what is the relation between Cp and Cv? So in that situation, you have to take this for 1 gram, right? This is for 1 gram you have to take, and here also you have to take for 1 gram. So unit of this Cp and Cv will change. Unit of the Cp and Cv will change. So what is the relation? Cp minus Cv is equal to R by or you can write, we can write here 1 by m molar mass of the gas into R. So this is for 1 gram of gas. For n mole of gas, this is for 1 mole of gas, and this is for 1 gram of gas. How to I mean convert this formula for 1 gram? You can see in all these cases the unit of the Cp and Cv are different. See, in the first case, what is the unit of Cp and Cv? I am writing here joules per Kelvin per mole, right? So this is the unit. Whether you take CP or CV, both have same unit. So in the first case, this is the unit. In the second case, the unit is joules per Kelvin of CP or CV, right? And in the third case, the unit is joules per Kelvin per gram, right? So if you want, you can check unit of left hand side and unit of right hand side should be same. So here the unit of R is joules per Kelvin per mole. Here see joules per Kelvin per mole into n moles. So mole and mole cancel. So joules per Kelvin. So here the unit of this CP and CV basically this is I mean joules per Kelvin, right? And here joules per Kelvin per gram, joules per Kelvin per gram, and here see unit of R is joules per Kelvin per mole, right, divided by unit of molar mass grams per mole. So per mole cancel. So the unit of right hand side is also joules per Kelvin per gram. So joules per Kelvin per gram, joules per Kelvin per gram. So this is the unit. So through this you can understand this is for 1 mole of gas, this is for n mole of gas, and this is for 1 gram of gas. There is a relation between CP and CV, right? So this formula, simple formula, is called Mayer's formula. Mayer's formula, right? This is called Mayer's formula. So CP and CV, these are I mean two different kinds of specific heat for gases, and this difference is due to the different path. In one case we are taking constant volume path, and in other case we are taking constant pressure path, right? Okay, so hopefully all of you are, all of you have understood what is CP, what is CB, and how they are related, right? And see, I'm recalling one formula what I have given you, the dependency of internal energy. If you see here, this formula. This delta E by delta T at constant V, this is equal to CV, you can say, because this in place of E we can put Q. So del Q by del T at constant volume, this is called CV. This is called CV. So we will talk about this CV, relation between internal energy and CV. What is a relation, right? So this internal energy of any system, basically it is defined as delta E is defined as basically delta Q at constant V. This formula is applicable everywhere, and we can say this is a master formula, but not for chemical reaction. I am taking a different view here. This formula is applicable everywhere, but not, right, not for chemical reactions. Okay, this formula you cannot use for chemical reactions, not for chemical reactions. chemical reactions, right? For chemical reactions, we define this internal energy change in a different manner, and I will explain you very clearly when time will come. Similarly, delta H is equal to this. This is again very important formula, but again this is not for chemical reaction. Means for any physical process you can use this formula. So what is change in internal energy for any physical process? Very simple. The change in internal energy is the net heat change at constant volume. And what is enthalpy for any physical process, not for chemical reaction? How it is defined? Very simple words you can use. The enthalpy is nothing but means unit of enthalpy and internal energy is same. Both are the form of energy, but one is at constant volume, other is at constant pressure, right? So delta E is equal to delta Q at constant volume and delta H. So internal energy change we can write here, internal energy change is equal to the net heat change. See, these are the core concept of thermodynamics, right? Net heat change at constant volume, right? For physical process, not for process, right? Not for chemical reaction. And enthalpy, delta H is called enthalpy. So enthalpy. So see, this is the reason why this thermodynamics we study in two parts, one for physical process, other for chemical reaction. The same function is defined in a different manner for chemical reaction. And if you are not able to differentiate, you are not able to understand this thermodynamics. See, same internal energy. Internal energy is defined for chemical reaction in a different manner. You cannot say that for any chemical reaction, internal energy change is equal to heat change at constant volume. Okay, this is equal to heat change, but some other rider will also be applied here. Now, this enthalpy change is equal to net heat change at constant pressure. This is for physical process. Listen carefully and try to understand. So now you can write delta E is equal to NCV delta T. This is the master formula. Irrespective of the type of process, which type of process is given, isothermal, adiabatic, isobaric, isochoric, whatsoever, if you are able to find out the CV and delta T, you can evaluate the delta E. this formula is the independent of any other factor. Similarly, delta H, this is the master formula. These are the master formula. Delta H is equal to NCP delta T. You can use everywhere this formula, right? Now some other formula we can derive from this. All those formulas may have some restriction that in this situation we can use or not, but this formula, whatsoever type of process, whatsoever the condition is given, if you have the quantity means number of moles, if you have the value of CV, and if you have the temperature change, you can calculate very easily this internal energy change, right? So here you can write for 1 mole of the gas from this equation, you can write CV per mole is equal to change in internal energy per unit change in temperature at constant volume. See, whatever I have stated here, that is I have represented here, and similarly Cp is equal to del H by del T at constant T, right? So this formula and this one, both are same formula for 1 mole. This is written, I have written for 1 mole. So Cv is equal to this and Cp is equal to this, right? This is equation 3 and equation 4, right? So Cp and Cv you can calculate by just seeing the nature of what gas. I have already told you how to calculate the energy. If you are able to calculate the energy of any gas, then energy by temperature, this is what Cv, and if you have the value of Cv, not need to calculate this delta H. Cp minus Cv is equal to R, you can use and calculate the value of Cp, right? Now, so suppose that if we take helium, monoatomic gas, helium, a monoatomic gas. So what is the total energy of this? The total energy of this is at room temperature or at temperature T is equal to 3 by 2 RT. This is the total energy of this. All of you are knowing 3 is the translational degree of freedom, and per degree of freedom half RT energy is associated. So for helium, this is what? Monoatomic gas, helium or any monoatomic gas, the total energy is equal to this. So what is Cv? You divide this with T. So Cv is equal to, you can write 3 by 2 R per mole. See, del E by del T at constant V is Cv is equal to 3 by 2 R. So for every monoatomic gas, you have Cv is equal to 3 by 2 R. Okay. So what is Cp? All of you are knowing Cp minus Cv is equal to R. And if you have Cv is equal to what? 3 by 2 R. So Cp is equal to R plus 3 by 2 R is equal to 5 by 2 R. So Cp for all monoatomic gases is equal to 5 by 2 R. So this is for helium, for neon, for argon, for krypton, xenon, radon, for all monoatomic gases. And this is also for helium, neon, argon, krypton, xenon, radon. For all monoatomic gases, this is always true. Now, Okay. Now see, if you take diatomic gas, diatomic, diatomic. So diatomic gas is always linear. So diatomic gas like hydrogen, oxygen, nitrogen, halogen, suppose that if we are taking this type of gas, then what is the total energy? So E translational is equal to 3 by 2 R. E rotational is equal to linear, so sorry, RT, 3 by 2 RT, and 2 into 1 by 2 RT, E rotational. And vibrational at room temperature, you if you want you can calculate, include, and if you don't want you cannot. So I mean, normal at room temperature, if we consider at room temperature where we are not considering the vibrational energy, so the total energy at this, total energy is equal to 3 by 2 R, 3 by 2 RT plus RT. So 3 by 2 RT plus RT. So this is equal to 5 by 2 RT. So CV is equal to 5 by 2 RT. Sorry, R. 5 by 2 R. So for diatomic gas, CV is equal to 5 by 2 R. So CP is equal to 5 by 2 R plus R. So this is equal to 7 by 2 R. So Cp is equal to 7 by 2 R for all these gases at room temperature or around room temperature. But at high temperature where vibrational is contribute, at high temperature. So when vibration is also included, so for diatomic like hydrogen, oxygen, etc., how to calculate? E translational is equal to 3 into 1 by 2 RT. E rotational is equal to 2 into 1 by 2 RT. And E vibrational, if you are including vibrational, so what the degree of freedom vibrational? 2 to the 4, 3 to the 6, 6 minus 5, 6 minus 5 means RT, 1 RT, right? You know vibrational will contribute RT. So what is the total energy? E total is equal to 3 by 2 RT plus RT plus R, right? Although this calculation is always, I mean, we prefer this calculation, but sometimes, so this is 2RT, uh, 7 by 2R, right? E total. So CV is equal to 7 by 2R. Seven by 2R. So CP is equal to 7 by 2R plus R, 9 by 2R. CP is equal So until or unless it is not given in the question that you have to include vibrational contribution of vibrational energy, you don't consider this, right? So the clue is given in the question whenever you are doing the question. Now see, triatomic or polyatomic we can say, and linear. Triatomic, triatomic, linear, like carbon dioxide. So I am directly writing E total is equal to E translational plus E rotational. I am taking this 2 only. So this is 3 by 2 RT plus linear. So 2 into 1 by 2 RT is equal to 5 by 2 RT. So CV is equal to 5 by 2 R, right? But CP is equal to CP is equal to 5 by 2 R plus R 7 by 2 R, right? So for triatomic linear like carbon dioxide, your CP and CV are like this. And triatomic non-linear, triatomic non-linear, like ozone, sulfur dioxide, etc. So for this, E total is equal to E translational plus E rotational. So this is 3 by 2 RT plus 3 by 2 RT. So this is equal to 3 RT, right? So CV is equal to 3R, and CP is equal to 3R plus R is equal to 4R. So in this way you can calculate the CP and CV, right? Now there is one more formula we have, that is atomicity. Atomicity. It is represented by gamma, right? So atomicity, it is defined as gamma is equal to Cp by Cv, right? Gamma is equal to Cp by Cv. So for monoatomic, gamma is equal to 5 by 2 R by 3 by 2. So this is equal to 5 by 3. For diatomic, gamma is equal to, what we have the value of Cp and Cv, normal temperature, not high temperature, 7 by 2R and 5 by 2R. So 7 by 5, right? For triatomic linear, gamma is equal to 7 by 5, I think, same. Triatomic linear, 7 by 2 or 5 by 2 or 7 by. And non-linear, triatomic, non-linear, gamma is equal to 4 by 3, right? So 5 by 3, 1.66, this is 1.66, and 7 by 5, 1.4, this is also 1.4, and 4 by 3, 1.33, right? So in this way you can calculate the atomicity or gamma, right? So this is all about the calculation of Cp, Cv, difference between Cp and Cv, and relation between Cp and Cv for different gases, right? Okay.